Assalamu alaikum students. Welcome to our another online session for the course Digital Logic Design. This session is specifically designed for the students of BCS 3A and this is lab 6, and in this lab we will be covering sequential logic design, specifically how to design a flip-flop using Verilog HDL. So let us first see the content which we will be covering in today's lab session. First of all, we will be having some introduction of the sequential circuits. Then in our previous lab we have discussed about latches, and in this lab we will be discussing a flip-flop basically. So this is the change as far as the previous lab implementation is concerned. Here we will be discussing instead of latches we will be discussing flip-flops. And at the end we will be having a demonstration that how we will implement that flip-flop, that specific flip-flop. Basically we will be implementing the D flip-flop using gate level modeling. So as far as the reference settings and acknowledgements are concerned, we are still at chapter number 5 of the book Digital Design with Introduction to Verilog HDL by Maurice Mono. So till now what we have studied about combinational circuits, and we have decided and we have discussed that the combinational circuits are the circuits that don't contain any memory element or any feedback element, and the output is only and only dependent upon the inputs. And we have implemented such circuits as like adders, subtractors, multipliers, encoders, decoders, multiplexers, demultiplexers. These were the prime examples of the combinational circuit, in which we will basically apply the input at any time instant, and the output we will observe the output with respect to input. So output is a function of inputs and inputs only, and we don't have any prior history or the memory element or feedback element that is involved in combinational circuits. Whereas as far as the sequential circuits are concerned, sequential circuits are basically implemented with the help of combinational circuits, but the difference is that now the output is not only simply dependent upon inputs but also on a previous history, and there exists a feedback path in the sequential circuits. A memory element is involved that basically stores your current state, and that current state, basically the output is dependent upon the inputs and the current states in which circuit is operating in order to determine the next state and the next output. So the inputs and the current state, basically they used to determine the outputs and the next state, whereas in the combinational circuit output is only and only dependent upon inputs. We have discussed that these sorts of circuit are being distributed into two categories: either they are synchronous circuits or they are asynchronous circuits. And in synchronous circuits the transition happens at discrete instant of time, whereas in asynchronous circuits the transition happens at any instant of time. Whenever there is a change in an input, the output is being updated in that particular way. The synchronous sequential circuits, this is the prime objective of today's lab. Basically we will be implementing the synchronous circuits. A master clock generator is required. That is the basic requirement of the synchronous circuits, to generate a periodic train of clock pulses. Why these clock pulses are required? Because we have to synchronize our output with some clock event, and in order to achieve synchronization these clock pulses are distributed throughout the system, and basically these sorts of circuits are commonly used, and these sorts of circuits have no instability or metastability problem. The memory elements that are implemented in that particular configuration are flip-flops, that are basically the binary cells that are capable of storing one bit of information, and they normally contains two output. One is in original format and one is in a complemented format, and they will maintain the binary state indefinitely until directed by the input signal to switch the states, and also the supply that has been applied to the circuit. Well, this is figure 5.2 of synchronous clock sequential circuits, in which you can see that and the memory element is being replaced by a flip-flop basically, and these flip-flops are basically triggering on some specific clock events, and so we have to provide those clock pulses to the flip-flops, and these clock pulses are basically the periodic frame, that have some set duty cycle and have some set frequency and time period. And we can see that these clock pulses contain some important information, either these levels in which the transition can be done. So this is high level and this is low level, or these edges, this is the leading edge or the rising edge of the clock, and this is the trailing or the falling edge of the pulse of the clock. So either we can achieve the synchronization by levels, or we can achieve our synchronization by synchronizing a circuit with these edges. So edge-based synchronization is most commonly used, and the transition to the outputs happens on that specific edge of the clock. Either it's a positive edge or the rising edge, or it's a negative edge or the falling edge or trailing edge. Now let us see the example which we have to implement in today's lab session. Basically, in today's lab session we will be implementing the D flip-flop, that is positive edge triggered flip-flop. So the transition only happens with the positive edge of the clock, and this is the diagram showing the implementation of the D flip-flop. That is basically implementing with the help of SR latch, which we have implemented in a previous lab. So we can see that the setup of the latch here, and there is also a set of the latch here that is repeated, and same is the case here. So we can implement a D type positive edge trigger flip-flop by using latches only, or we can also implement this diagram by using gate level modeling instead of implementing this latch first. So if you have implemented this latch, and because you have already implemented the latch in the previous lab, what you can do is you can instantiate this latch in your flip-flop module, and you can make interconnections, so you don't have to regenerate the code again. But you can also implement that from scratch if you are not willing to instantiate or reuse your previous lab codes. So what you have to do is you have to make a module containing the description of a D flip-flop and implement this diagram, but you have to make sure to label the interconnections or to define the wires properly, because here you can see that there are a bunch of wires which you have to define in order to make interconnections between these gates. Now the next important thing, that the most important thing that is that how we will going to generate this clock source in Verilog HDL, and there are several ways to generate the clock using Verilog HDL. So let us first see how many methods are there in order to generate the clock. Then we will move to the model sim, and we will see the basic structure of our D flip-flop and the test bench that is used to test our D flip-flop. And in this lab session basically you will be implementing this diagram, and you will be simulating a D flip-flop in order to see how the synchronization is made and how Q and Q prime are related to D. But first of all, let us see the clock generation mechanism, and let us go to the book. This is chapter number 5, page 218, and here we can see the variety of codes in order to generate the clock. First of all, let us see this specific code. Either we can use this portion of code, or we can use this specific portion of code uh, that is separated by this line. Basically, in the previous code we are using the initial block. Basically we are defining these terms and these routines in our test bench basically in order to provide the clock to our main module. So we start with the initial block. This is begin and end, and first of all we have to define our clock to 0. We have to reset our clock, so clock equals 1 tick be 0. Then we are using the repeat primitive, so 30 times this thing will be repeated, and a clock will be complemented after each 10 time frames. So whatsoever the time frame is, let us assume that the time frame is in nanoseconds. So after each 10 nanoseconds, the clock is complementing itself. So the period of the clock is 10 nanoseconds high pulse and 10 nanosecond low pulse. So the total period or the total time period for the clock is 20 nanosecond, and frequency of that particular clock is 1 over t, that is 1 over 20 nanoseconds basically. That is basically 1 megahertz. So we can also generate the clock here. In this particular time frame, the duty cycle of each clock source generated is 50%, because half of the time the clock is high and half of the time the clock is low for the total time period. We can also generate our clock in the same way that uh, we are using two initial blocks and one always block here. First of all, the first initial block is setting the clock to 0, and then we are using initial block for the 300 time frame, and this simulation will run for the 300 time frame, and it will finish. And for all those 300 time frame, after passing of each 10 time frame, the clock will be complementing itself. So both of the codes are basically same and similar, but the difference is that here in this particular way the simulation will end after 300 time frame. So basically it is equal to the 30, you can say that repetitions here, and you can see the clock and with the same period here. So both of the codes are equivalent in order to generate the clock. Let us see a clock that is forever running till that time our simulation is running, and we can see that we have defined an initial block here. While setting the clock equals to 0, you can also use 1 tick b0, both are equivalent. And then we are using forever block setup, forever block here, and hash 10 is a 10 time frame delay, and clock is complementing itself after each 10 time frames. So this portion will execute for forever, and unless and until you stop your simulation, the clock is generated each 10 time frames. The clock is complementing itself. So here also the time frame or the time period for the clock is 20 nanoseconds. For example, our time scale is set to nanoseconds. So you've got all the three ways in order to generate the clock here. So in your test bench, basically you will gonna use either this piece of code here, or you can use this forever method in order to generate your clock. Now let us go to the model sim and let us see the basic structure of our setup, and we'll see how we're going to define our clocks here. So first of all, we're going to create our project with new project. Yes, we are closing the current project, and we are naming it as lab 6. And the location of the project is, basically we are creating a new folder here named lab 6, and selecting that folder and setting it OK. The next thing is we have to create the files. So our first file is DFF for the D flip-flop. You can name it according to that, or whatsoever the name you see convenience in naming. And the type of this file is Verilog, and press it OK. And we are creating another file that is D flip-flop D underscore D flip-flop, and file type is Verilog, and press it OK and close. Now coming to our main file, that is module, and defining the basic structure, what will be the port list and the interconnections which you have to use in your lab session. So we'll define the keyword module, the flip-flop, and inputs are D clock, and outputs are Q and Q prime. And then we're gonna end this with end module. Now we're going to define our inputs. Input is D and clock, and outputs are Q and Q prime, QP. Now what you have to do is that first of all consider that diagram which we have discussed earlier in our session, and just see the interconnections that are required to interconnect the gates, because we have to define wires here if we are not using that SR latch which we have implemented, and in the same case we do also need to define some wires here. So properly label your wires and define your wires here properly, and then provide the description, the gate level description here in your main module file. So this basic structure you have to use in order to define your D flip-flop. Now let us see the test bench, and the test bench here starts with module, that is T underscore D flip-flop and semicolon, and we're gonna end this with end module, and then we have to define our inputs as reg. So reg D and clock, and wire Q and Q prime. Then we have to instantiate our module, so that is D flip flop, D flip flop first instance and then the port list, that is D clock, Q and Q prime. Now we have to define our inputs. So first of all, let us define the clock. So we can use either method to define our clock. I am using the initial block, begin and end of this first initial block, and in this initial block I am using first of all clock equals 0, or you can say that 1 tick B0 and then I am using the forever block, forever primitive, forever hash 10 clock is equal to not clock, and this is the setup to generate our clock source, which we have already discussed here in our description. So this initial block basically is a clock source generator, that is the clock source generator. Now let us define another initial block for our setup inputs. So we'll start with another initial block. Begin and end of this initial block, and here we will be setting our inputs. So for example we are setting D equals 1 tick B 0, then after the time delay of 5, we are setting D as equals 1 tick B 1. Then after the time delay of 10, we are setting D equals 1 tick B 0. Then after again hash 10, we are setting D equals 1 tick B 1. Then after again 10 time frame, we are setting D equals 1 tick B 0. Then after spending 5 more time delays, we are setting D equals 1 tick B 1. And then after 15 time delay, basically we are generating a random waveform to see what would be the effect of synchronization on that particular waveform. D equals 1 tick B 0, and then after 5 time delay, we are setting D equals 1 tick B 1, and so on and so forth. You can test the remaining combinations. You can define your waveform of D according to your will. So these are the pattern I want to check. Basically I want to observe the synchronization, and let us see after defining our module that how our output is basically affecting or changing with respect to inputs and the clock which we have defined here. So this is the basic test bench here, and you're going to provide the description of your module here, and you're gonna provide the timing simulation, the waveform, timing waveforms, in order to provide the functional simulations here to verify the functionality of the D flip-flop. So this is the end of our lab 6. In our practice session, you will be basically demonstrating the concept of D flip-flop and implementing that D flip-flop using Verilog HTL, and providing your result and verifying the concept of synchronization here. Well, this was our last lab session as far as the implementation is concerned. And our remaining lab sessions are specifically assigned or reserved for your project. So if you got any queries regarding your project implementation, that have been assigned to you in groups, and that groups are already discussed with you and your class representative. So if you got any queries regarding your project implementation and the description and the modules and or the components of the project, and how you're going to approach that project, how you're going to conceive that project from scratch till implementation and verification, we will be discussing that in our remaining lab sessions. So thank you, students. This is all for today's session. I hope so you will be able to understand the concept of synchronization and implementation of D flip-flop in order to store a single bit, and the remaining sessions we will basically implementing our project. We will be implementing our project, and if you got any queries regarding your project, we can discuss that in our remaining lab sessions.